A single rack of modern AI servers can, draw over 100 kilowatts of power.
Which is just a staggering amount of energy.
Right. I mean, that is literally enough electricity to run an entire neighborhood. And more importantly, it runs hot. Like
Yeah.
hot enough to literally melt the copper interconnects inside of it if the liquid cooling systems fail for just 30
Yeah,
seconds.
30 seconds all it takes for millions of dollars of hardware to basically cook itself.
Exactly. So, welcome to today's deep dive. We are totally thrilled to have you with us today. You always see the photos of these immaculate, sci-fi looking data centers.
Oh, yeah, the ones with the blue LEDs and pristine aisle.
Right. And it's so easy to get mesmerized by the sheer brute force muscle of thousands of GPUs. But the reality is we are still trying to manage these massive hyperscale systems with, well, operational mindsets built for the dot-com era.
Which is a recipe for a very expensive disaster, honestly. Because as these data centers scale up to handle massive workloads like training 100 billion parameter large language models, the risk of a catastrophic failure scales right along with them.
It really does.
Today, we're going to explore why the software orchestration running the data center is just as critical and, frankly, just as complex as the silicon itself.
Yeah, to figure this out, we got our hands on an internal 2026 training document from Supermicro. It details their SuperCloud software suite, which is designed specifically to manage these intense GPU-accelerated AI workloads.
It's a fascinating read.
It really is. Okay, let's unpack this because right off the bat, the document establishes a core design philosophy, which they call independent but integrated. I mean, it's essentially a modular stack.
Yeah, it's an acknowledgement that you just can't force a data center to rip out their entire legacy infrastructure, right? You can't just install one giant monolithic piece of software.
It's way too risky.
Way too risky. So this Supermicro suite is broken into 4 distinct modules. They act almost like a survival guide for operating at scale.
So let's start with the most basic survival skill, which is observability. There is this visual comic in the training document that just perfectly illustrates the problem. They call it an alert storm.
Oh, man. Every data center admin's absolute worst nightmare.
Exactly. So the comic shows an operations room, and the screens are just a cascade of flashing red alerts.
Total chaos.
Right, but because traditional systems rely on all these different protocols, I mean, you have SNMP for the network, IPMI for the servers, Modbus for the cooling, there is zero correlation between them.
Not at all.
So the admins are physically walking down the aisles, they're checking racks manually, guessing if a server melted down because of a software logic error, or if, the cooling pumps simply gave out.
And at the scale of a modern AI data center, physical proximity just doesn't help you. You need a centralized brain to parse through all that noise.
Right. And the document introduces the first module for this, which is SuperCloud Composer, or SCC. It is pitched as a single pane of glass for real-time health, power, and thermal monitoring.
It's incredibly granular, too.
Yeah, it tracks power usage effectiveness, or PUE, down to the component level. So it's not just telling you the building's overall power draw.
Right. It's reading the telemetry off the CDUs.
The cooling distribution units. Right?
Exactly. The unit's pumping chilled liquid directly to the cold plates on the actual chips. And it correlates that with the memory power draw on a specific motherboard.
But wait, I have to push back here. In the middle of an alert storm, throwing more telemetry at an admin doesn't really solve the core issue, does it?
How do you mean?
Well, if my GPU rack is hitting critical thermal mass, a blinking red dashboard, even a highly detailed one, doesn't actually put out the fire. So is this just a giant glorified visualization layer?
Ah, I see what you mean. What's fascinating here is that SEC is actually built around policy-driven localized automation. It's not waiting for a human to interpret that dashboard.
Oh, so it acts on its own.
Exactly. Let's look at the liquid cooling mechanics we just mentioned. If SEC detects a pressure drop in the coolant loop on a specific node, which obviously indicates a leak, it doesn't just shoot off an email.
That would be bad.
Right. It acts almost like a biological immune system. Based on preset policies, it instantly initiates a graceful shutdown of that specific workload.
Wow.
Yeah, it isolates the node, and it immediately disables the smart PDU outlets to kill the power. And it reacts in milliseconds, completely preventing a catastrophic short circuit across a multi-million-dollar rack.
Okay, so it's effectively a reflex arc. It just bypasses the human entirely for those critical survival functions.
Precisely. And if we connect this to the bigger picture, This kind of closed-loop telemetry unlocks something the document calls power asset orchestration.
Which sounds intense. What does that actually mean?
Well, AI clusters consume so much power they can actually destabilize local city grids. So SEC monitors energy pricing and availability in real time.
Really? Like live utility data?
Yep. It can automatically shift non-critical compute loads between the commercial power grid and a private smart grid, like on-site battery storage or solar panels.
Oh, that's smart.
Yeah, it's doing demand response and peak shaving autonomously,
Mm.
based entirely on carbon awareness and cost optimization.
So it's dynamically optimizing the data center's power bill. That is incredible. But preventing fires and optimizing power only solves the baseline physical layer, right?
That's just keeping the lights on.
Exactly. Once you establish that stability, a totally new operational bottleneck emerges, which is provisioning. How do you scale up? The source text makes it clear that manually setting up 1,000 new AI servers is just completely untenable.
Oh, it's the exact point where traditional IT completely breaks down.
Right.
I mean, imagine you get a request for a 500-node training cluster. Historically, an admin literally pulls the servers, cables them up, flashes the BIOS, configures the RAID arrays, and installs the OS one by one.
That sounds like a nightmare. And the document points out that 500 nodes basically means 500 times the risk of human error.
Which is virtually guaranteed at that scale.
Right, which naturally brings us to the second layer of the modular stack, SuperCloud Automation Center, or SARI. It's designed to turn that manual provisioning nightmare into a single-click workflow.
Whether you're deploying a Kubernetes cluster or, say, a Slurm workload for high-performance computing.
Right. But here is where I get a bit tripped up by the source text. The document explicitly states that SSAG does not replace DevOps tools like Ansible, Terraform, Chef, or Puppet.
Correct.
So if a company already has massive libraries of automation scripts in Terraform, why do they need SSAG? Isn't this just adding another manager to manage the managers? Like, doesn't that introduce more latency?
That is a great analogy, but there's a vital distinction here between execution and orchestration.
Okay, how so?
Tools like Ansible or Terraform are fantastic at executing specific tasks. But at a massive scale, relying on a patchwork of individual scripts is like trying to fly a supersonic jet by manually pulling cables attached to the flaps.
Okay, I can see that. So what is SSAG doing differently?
SCAD acts as the fly-by-wire system. It interprets the broad command like build a 500-node cluster and translates it into thousands of micro-adjustments across the hardware seat.
How does that actually work mechanically, though? What is it doing that Terraform just isn't?
Let's look at firmware drift.
Yeah.
Every single server has a baseboard management controller, or a BMC.
Right, that's the tiny independent mini computer on the motherboard, right?
Exactly. And it runs even when the main server is completely powered off. Over time, across 10,000 nodes, those firmware versions start to drift.
Just from normal operations.
Yeah, patches fail, nodes randomly reboot, and suddenly you have different network card or GPU firmware scattered across your cluster. Terraform, by default, assumes the underlying hardware is identical.
Ah, so when Terraform tries to run its scripts, it just fails because the foundation is mismatched.
Exactly. SK constantly pulls the bare metal layer via Redfish APIs. It detects that drift, and it actually forces the hardware back to a baseline state before it allows the execution tools to install the OS.
Oh, I see. So it's essentially guaranteeing the foundation is perfectly flat before it lets the builder start pouring the concrete.
That's a perfect way to put it. And the document highlights another critical mechanism here, which is secure injection.
Right, managing secrets.
Yeah. In typical DevOps pipelines, managing passwords, API keys, and certificates across thousands of nodes usually results in humans hard-coding secrets somewhere they really shouldn't.
Like leaving a Post-it note with the password on the monitor, but digitally.
Exactly. SK acts as a centralized vault. It injects dynamic, short-lived secrets directly into the workflows. It orchestrates the entire factory line without a human ever touching a static password.
Okay, so we've got the hardware stabilized with Composer, and we've got the provisioning totally automated via the fly-by-wire system in Automation Center. But once that cluster is spun up, human politics come into play.
Oh, they always do.
You have different internal teams or entirely different companies fighting over these incredibly expensive resources.
And let me tell you, they do not want to share. This is where the challenge transitions from managing physical infrastructure to managing multi-tenant sovereignty.
The source outlines this common nightmare scenario. So, two competing research teams need dedicated AI clusters. Without automated tenant isolation, the data center admin physically racks the servers, right?
Right.
Then they have to manually hand off a ticket to the network admin to configure the switch ports and the VLANs to ensure the networks are isolated.
A completely manual handover.
Exactly. And if that network admin fat fingers a single configuration, you've just accidentally bridged the network traffic of two competing corporate entities.
Which is terrifying. In the enterprise AI world, a data breach like that isn't just a minor IT failure.
No, it's a massive legal and compliance disaster.
Exactly.
So to solve this, the stack introduces the third module, SuperCloud Director, or SCD. It uses an OpenStack-based control plane.
Yeah. Specifically, it leverages OpenStack Ironic for the bare metal provisioning and OpenStack Neutron for the network segmentation.
Right. It dynamically programs the physical switch ports using the pre-boot execution environment, or PXE boot, to deploy the isolated infrastructure entirely through software.
Meaning that dangerous manual handover between the server team and the network team is completely eliminated.
Right. But I have to ask, why go through all this trouble to automate bare metal servers and physical switch ports? Why not just spin up standard virtual machines?
It seems easier, right?
Yeah, I mean, we've been using VMs to isolate tenants in cloud environments for over a decade.
It's a fair question, but AI workloads fundamentally break the virtualization model.
Really? How?
Well, when an enterprise is training a proprietary foundation model, they require absolute maximum throughput. A hypervisor, the software that actually creates the virtual machines, introduces a tiny bit of latency.
Oh, okay.
In a standard web server, you'd never notice it. But in a massive distributed GPU training run, that hypervisor overhead cascades. It ends up slowing down the entire job by days.
Wow, days. And plus, I guess if you are sharing a physical server using VMs, you also have the noisy neighbor problem.
Exactly. Even if you are logically isolated in a VM, you are still fighting for bandwidth on the exact same physical PCIe. If the other VM spikes its data transfer, your GPU gets starved of data.
That sounds infuriating if you're paying thousands of dollars an hour for compute.
It is. Furthermore, highly regulated industries like finance or healthcare simply cannot accept the security risk of a hypervisor vulnerability leaking data across the CPU cache.
So they demand absolute physical isolation. They want the entire server chassis completely to themselves.
Yes. But they still want the experience of the public cloud. They want to click a button and just have it instantly available.
Right, they want their cake and to eat it too.
Basically, yeah. And SuperCloud Director bridges that gap. It provides the self-service, automated delivery of the cloud, but strictly provisions secure, hardware-isolated bare metal.
Okay, so think of it like this. Instead of a traditional cloud where everyone is renting a room in the same shared apartment building, SCD is basically dropping a fully functional, completely isolated tiny house onto the property for each customer.
That is a brilliant analogy. Yes, exactly.
Okay, that makes perfect sense. So the infrastructure is physically segregated, the networks are locked down, and the foundation is laid. But ultimately, the people actually doing the work the AI developers need to write code.
They need to actually test their models.
Right. Which brings us to the final piece. SuperCloud Developer Console, or SDX. And here's where it gets really interesting, because we're not just talking about technology anymore.
No, we're talking about pure economics. The developer experience directly dictates the return on investment for the entire data center.
Exactly. So the document details how SDX manages GPU allocation. It doesn't just hand out full access to an 80-gigabyte GPU.
Right, which would be massive overkill for a lot of tasks.
Yeah, instead it utilizes dynamic partitioning. It can take a single massive GPU and slice it into smaller hardware partitions, say 10% or 20% chunks.
Allowing multiple developers to run lightweight inferences or, Jupyter Notebook experiments simultaneously.
But wait, if I'm a developer, do I actually care about dynamic partitioning? Don't I just want my Jupyter Notebook to open so I can run my experiments?
Oh, the developer might not care, but the business absolutely does.
And plus, if you are slicing an 80 GB GPU into 10% chunks, doesn't that introduce terrible latency? I mean, if I'm sharing the physical bus with 9 other workloads, how do I not notice a massive performance hit? Or worse, VRAM fragmentation.
That is a highly perceptive question, and is exactly why SDX doesn't do this with software. It relies on hardware-level partitioning protocols.
Like what?
Like NVIDIA's MIG, multi-instance GPU, or SRIOV. It is not doing software virtualization where workloads are, taking turns.
Oh, so it's happening at the silicon level.
Yes. It is physically isolating the GPU memory and the compute cores. Each partition gets a dedicated, guaranteed slice of the memory bandwidth.
Oh, wow.
So to the developer's container, it looks and acts exactly like a physically distinct, smaller GPU. There is zero noisy neighbor problem and no performance hit within that allocated slice.
That is incredibly clever. It's physically dividing the hardware, not just scheduling it. And the document also points out that SDX has multi-vendor support, right?
Yeah, across NVIDIA, AMD, and Intel Gaudi.
Which gives data centers incredible flexibility to avoid vendor lock-in.
But this raises an important question. Beyond just technical flexibility, why is this level of granular slicing so critical to the business?
It's all about the FinOps, the financial operations. I mean, an AI node with 8 high-end GPUs costs hundreds of thousands of dollars.
Right.
The CFO does not want a developer requesting a full 80 GB GPU, running a simple 5-minute test script, and then leaving that hardware locked and idle while they go to a 2-hour planning meeting.
Because that idle time is literally burning capital. It is arguably the single biggest inefficiency in AI development today.
And SDX addresses this directly. It acts almost like a high-frequency standard exchange for compute power.
I love that comparison.
Yeah, it has built-in token-based billing and auto-reclaim features. It actively monitors the telemetry coming off the workloads.
So if it sees a developer's allocated partition sitting idle, it doesn't wait for them to log off.
Nope. It automatically reclaims those GPU resources, pauses the state, and immediately hands the compute power to the next workload waiting in the distributed training queue.
It utilizes queuing theory and quota competition. It actually allows the business to safely over-provision the cluster.
Because they know statistically that not every developer will be computing at 100% utilization simultaneously.
Exactly. It ensures the hardware is constantly fed with data, maximizing the financial investment while still giving developers the self-service access they need.
So what does this all mean? We've traced the entire journey of this 2026 SuperCloud software suite. We started with Composer, which acts as an immune system to prevent thermal meltdowns and optimize power grids.
Then we moved to Automation Center.
Right, acting as the fly-by-wire system to prevent firmware drift and enforce secure deployments. Then we saw Director use OpenStack to give competing tenants bare metal isolation without the noisy neighbor problem.
And finally, Developer Console physically slicing up GPUs to ensure idle resources don't bankrupt the enterprise.
It really reveals a profound shift. The era where hardware alone defined the capabilities of a data center is over.
It really is. Assembling the silicon is merely step one. The true differentiator, the thing that determines whether an AI factory is wildly profitable or a catastrophic liability, is the orchestration layer.
And the genius of the independent but integrated approach is that enterprises don't have to boil the ocean. If a company is bleeding money on idle hardware, they can just deploy SDX.
Right, or if they are paralyzed by alert storms, they just spin up Composer.
Exactly. They adopt exactly what they need to eliminate their specific operational bottlenecks.
And as we wrap up, I want to leave you with one final thought to mull over.
Oh, I'm ready.
Throughout this deep dive, we've examined how we are using increasingly complex software and automation to manage human-built infrastructure.
Right.
We are using these systems to compensate for human reaction times and manual errors. But as tools like Composer and Automation Center ingest billions of data points regarding thermal dynamics, power draw, and component failure rates,
Yeah.
how long until the AI orchestrating the data center realizes the physical layout of the racks is actually suboptimal?
Oh, wow.
At what point does this software nervous system begin writing the code to redesign the physical architecture of the data center itself, becoming entirely and autonomously self-optimizing?
That is a staggering thought. The software outgrowing the physical shell we built for it. Well, that's definitely something for you to keep in mind the next time you read a headline about a massive new AI supercomputer being built. Thank you so much for joining us on this deep dive.
It's been a pleasure.
Keep questioning the mechanics behind your everyday tech, and we'll see you next time.